Alright, in this video we are going to learn more convergent tests for series. So section 1.5, the ratio test, the root test, and comparison test. So let me first introduce you the ratio test. So now let's go to the statement. So this is the statement of the ratio test. So let summation a and b an infinite series with positive terms, and we let r to be limit of the ratio a n plus 1 over a n when n go to infinity. Then if the value of r lies between 0 and 1 including 0, then the series is convergent. If r is bigger than 1, then we conclude that the series is divergent. And if r is equal to 1, the ratio test is inconclusive. So that is the statement for the ratio test. The idea is here. When you define your r to be limit of a n sub 1 over a n, it means that you can approximate a n plus 1 by using r times a n's, and it does mean that you can approximate a n plus 2 by r times a n plus 1, and that is r times a n, which means a n plus 2 can be approximated by r squared times a n. And you keep repeating this thing, so at the end you're gonna get a n times 1 plus r squared plus dot dot dot. And this thing inside parentheses, this is a geometric series, right? So it does mean that your series gonna be convergent when absolute r less than 1. So that is the idea behind the ratio test. But when you just memorize the statement and use it, so you just need the thing in the box here. So let's start by looking at example 16, so you get more idea how ratio test works. So example 16, using the ratio test. So we want you to use the ratio test to check if the series converge. So let's start by question A. So I have summation of n over 2 to the n. So this is your first example for ratio test. So I'm going to show you the full solution. So let's start by an equal to n over 2 to the n. So for ratio test, an must be given like this. So you can see that it is given that an equal to n over 2 to the n. And then after that, well, before using ratio test, make sure that you have positive terms. So just mention a little bit that you already pick an and an is positive. So now you ready to use ratio test. So we know that this thing an is positive because n is always positive and 2 to the n is always positive when n is an integer, right? A positive integer. All right, next we're gonna compute our r, which is limit of a n plus 1 over a n. So r here, this is limit a n plus 1 over a n when n go to infinity, and this thing is limit of so let's go slow here. So a n plus 1 here, you replace n by n plus 1, so you have n plus 1 over 2 to the n plus 1. All right, and an here, what you have is you have n over 2 to the n. All right, and then after that you just need to simplify it. So I will have n plus 1 over n here, and then I will have 2 to the n over 2 to the n plus 1 here. Well, I just simplify it, And then after that, you can see that what you have left is just limit of n go to limit when n go to infinity of n plus 1 over n times 1 half, because 2 to the n gonna cancel with 2 to the n plus 1, and then you have 1 half left, right? Because 2 to the n cancel with 2 to the n. And then after that, you compute the limit. So this limit go to 1 half, right? So it's gonna be limit of n plus 1 over 2n, and this thing is 1 half, well, which is less than 1. So that means the series is convergent, because you can conclude it from here that when your r is between 0 and 1, so the series is convergent since r less than 1. This series is convergent. All right, that is easy and simple, right? So let's do 2 more examples so you get the idea of the ratio test. But we're gonna do the same pattern for every question. So let's start by pull out your an from the problem, and then say that an is positive, and then you compute your r, and then conclude the pattern of convergence from the value of r. All right, let's do part B and C here. So part B, you have summation of 10 to the n over n factorial, where n start from 1 to infinity. So here we have a sub n equal to 10 to the n over n factorial, right? And then we can see that an is positive always, right? Because 10 to the n is always positive, and n factorial cannot be negative. So, well, an is always positive anyway. So now we just compute our limit of an plus 1 over an. This is your ratio r. And then you have limit n go to infinity. So n plus 1 is 10 to the n plus 1 over n plus 1 factorial. And then a sub n is 10 to the n over n factorial. For those of you who are not familiar with this algebra, so please go slow, because you could make a mistake here. So what I am going to do is I'm going to keep 10 to the n plus 1 over n plus 1 factorial here. And then the thing in the denominator here, I have to move it to the regular line. So I'm going to swap n 10 to the n over n factorial to n factorial over 10 to the n, right? That is how we just make the notation looks easier. And then after that, I can do a cancellation. So 10 to the n gonna cancel with 10 to the n plus 1. So you have 10 left. And then n factorial gonna cancel with n plus 1 factorial. So you have n plus 1 left. Does it make sense? Because n factorial over n plus 1 factorial, this thing is n factorial over n plus 1 times n factorial. Because if you expand n plus 1 factorial, it's going to be n plus 1 times n minus 1 and so on. So that means n plus 1 times n factorial, and this thing cancel. So now you have left 10 over n plus 1, and this thing is 0, which is less than 1 as well. So this question is also convergent. So since r less than 1, the series is convergent, or the series converge. All right, next. So let's do part C. Here we have summation of n to the n over n factorial. So let a sub n to be n over n factorial. Good. And then after that, well, we can see that this thing is positive. So a sub n is positive. Right? Before using ratio test, we're gonna just check that we have positive terms only. And then after that, we compute R, which is limit of a sub n plus 1 over a n when n go to infinity. And that is limit of n plus 1 over n plus 1 raised to the n plus 1 power, and then over n plus 1 factorial. Multiply. So here I have a n plus 1 already. So the next thing I need to multiply 1 over a n, right? Which is n factorial over n to the n, right? So if you cannot follow this thing easily, so make sure you expand this slowly. And then after that, I am going to do the cancellation. So you can see that, first of all, my n factorial gonna cancel with my n plus 1 factorial, right? So I have n plus 1 left. So that means I have limit of n plus 1 to the n plus 1 over n plus 1 times n to the n. And then next I'm gonna do more cancellation. So n plus 1 gonna cancel one time with this thing. So what I have left is limit of n plus 1 to the n over n to the n when n go to infinity. And then after that, I have limit of n go to infinity, n plus 1 over n to the n, right? And that is limit of 1 plus 1 over n to the n when n go to infinity. Here you end up with the indeterminate form 1 to the infinity. So you have to apply the technique of L'Hopital rule again, right? Assume that we extend the domain. We extend the domain from natural number to real number. To real number. Well, the reason why I do this because we just want to apply the L'Hopital rule, and the L'Hopital rule works with real numbers. So we're gonna extend the domain from natural number to real numbers. And then after that, we need to compute limit of 1 plus 1 over x to the x raised to the x power when x go to infinity, right? And this thing, first of all, I'm going to take log of this thing, so I can swap limit and log. All right, and then after that, I can just move my x down. So I'm gonna have limit of x times log 1 plus 1 over x. And then after that, I have limit of log 1 plus 1 over x over 1 over x, right? And then I use L'Hopital rule. Now I can differentiate the top function and the bottom function. So I have 1 over 1 plus 1 over x times negative 1 over x squared. So this is by differentiate this thing. And then I differentiate 1 over x as well. So I have negative 1 over x squared. And then after that, I cancel this thing. So what I have left is just I have limit of 1 over 1 plus 1 over x, where x go to infinity, and this thing is just 1 over 1 plus 0, which is 1. You had seen this before, right? Because we compute limit when we learn sequence 2, and you can see that log of limit equal to 1. It means that just limit of 1 plus 1 over x raised to the x power, this is e, which means your r. So this implies that your r is equal to e. That means it is bigger than 1 because this is e is 2.7. So that means the series is divergent. So we conclude that the series is divergent. That's it. That's how we do the ratio test. Now let's move to the root test. So the root test has the same idea with the ratio test. So we're gonna let summation an to be an infinite series with non-negative term. So before you use the root test, just make sure that you figure out your an and say that the an has only non-negative terms. And then after that, you need to compute your rho, which is equal to limit of the n root of an, or in other words, it is limit of a sub n raised to the 1 over n power. And then once you get your rho, so this is how you conclude. So if your rho is between 0 and 1 including 0, you conclude that the series is convergent. If your rho is bigger than 1, then the series diverge. If your rho is equal to 1, then the ratio test is inconclusive. Well, that means you have to use other tests. Alright, so let's do example. So start by example 17. Alright, we want to use the root test to check the convergent pattern of this series. So part A, I have this thing. So we're gonna let an to be 2 to the n square plus 1 over n square plus 4 raised to the n power. And then you can see that an is always non-negative, right? Because you have n square here, which is always positive, right? 2n square plus 1 and n square plus 4. So this thing is always non-negative. And now you need to compute your rho, which is defined to be limit of the n root of a sub n when n go to infinity. And that thing is limit of the n root of 2n square plus 1 over n square plus 4 to the n. Right? And then you can see from here that the n root gonna cancel with n here. Right? So if you have a hard time to think about it, so you can say this is limit of 2n square plus 1 over n square plus 4 to the n power, and then the n root gonna be just raised to the 1 over n again. Right? This is the same thing, but I just switched the notation to make it cleaner for you. So you can see that n and n here gonna cancel. And then what you have left is just limit of 2n square plus 1 over n square plus 4. And this thing is just 2, right? Because you compute the limit, and well, when you have limit of polynomial over polynomial, so you can with the same degree, so you can just answer the coefficient as you answer. So it's 2 over 1, which is 2. This is a technique from Cal 1, and then this is bigger than 1. Alright, so since your rho is bigger than 1, so we conclude that the series is divergent. We conclude that the series is divergent. Alright, next part B. So let's do this question. So for this question, we're gonna let an to be n square over to the n, right? And this thing is always non-negative, so that is good. All right, now we compute rho, which is limit of a sub n raised to the 1 over n. So I'm gonna use this notation because it seems like it is more clean that way. So this thing is going to be n square over 2 to the n, right? And then raised to 1 over n thing. And then now it's a bit tough here because you can cancel something on the bottom term, right? But on the top term it is hard. So on the top term you're gonna have n raised to 2 over n, right? And on the bottom thing you're gonna have 2 raised to the n over n, because I just move 1 over n inside the parenthesis, right? And then after that I have just limit of n raised to the 2 over n over 2, right? When n go to infinity. This is because n and n cancel here. Now if I simplify a little bit, so I have 1/2 time limits of n raised to the 2 over n. This thing is indeterminate form again, right? So you have to use L'Hopital rule again. So this is infinity raised to the 0, which is indeterminate form again. So we have to use the L'Hopital rule. So assume we extend the domain to x and then we compute the limit. So we're gonna compute logarithm of limit of x to raised to the 2 over x. When x go to infinity, we're gonna compute this thing first. And then this thing going to be limit of log, so we can swap limit and log. Well, we have done this thing for several times, so you should be able to do this thing by your own now. So now you just need to compute limit of I am going to move 2 over x down, right? So I'm gonna have 2 over x times log x. And then after that I can pull out number 2 outside, and then I have limit of log x over x, right, when x go to infinity. And by using the L'Hopital rule, so we can differentiate the top thing and the bottom thing. So I have 2 times limits of differentiate log x, so I get 1 over x. Differentiate x, I get 1. So I have 2 times 0, right? Because limit of 1 over x when x go to infinity is 0, and that is 0. So that mean this mean limit of x raised to the 2 over x when x go to infinity is just e to the 0, which is 1, right? So we have this thing. So let's come back to the original question in green. So now your rho is going to be 1/2 times 1, because you already compute the limit and then you get 1, right? So and that means your rho is 1/2, which is less than 1. So we conclude that the series is divergent. Oh, sorry. The series. So we conclude that the series is convergent, because your rho is less than 1. All right, we are done with root test. All right, now let's move to the comparison test. So the comparison test is another technique to check the convergence or divergence of the series. But the hard thing for the comparison test is you need to know how to compare the a sub n and b sub n. This is the hardest part for the comparison test. So we're gonna first show you the statement and then gonna walk you through some examples. So let's look at the statement first. So for the comparison test, you're gonna have two series. So let's suppose that you have summation an and summation bn. Both are positive series. Well, the condition is right here. So if you have an inequality 0 less than an less than or equal to bn, and you know that summation of bn converge, then you can conclude that summation of an converge. So think of this in terms of picture. You have 0 less than a sub n less than b sub n, right? And then if you know that this thing is convergent, then it's gonna force an to be convergent too, right? Which does make sense. And then another one that I highlight in green here is if 0 less than bn less than or equal to an, and you know that bn diverge, summation of bn diverge, then you can conclude that summation of an diverge as well. So on the other hand, if you have 0 less than bn less than or equal to an, and you know that your bn is divergent, well, even the small thing is divergent. Well, when you have something that is bigger than the small thing here, so that thing is forced to be divergent too. That is how the comparison test work. But the hardest part is how to choose your bn. So let's do some examples. Alright, let's start by looking at example 18. So I have summation of sine square n over n cube, where n start from 1 to infinity. So when you see sine and cosine, well, let's use the squeezing technique because it should work, right? Because when you sine and cosine, you should bound it by -1 and 1. So we know that sine n, this thing gonna be in between -1 and 1 for sure, right? For all n. And if you do the square thing, so sine square n, right? This is going to be less than or equal to 1, but must be bigger than or equal to 0 because you put square thing on the sine function, and that means this function cannot be negative now. It must be non-negative. And then after that, if you divided everything by n cube, so now I have sine square over n cube less than or equal to 1 over n cube and bigger than or equal to 0 over n cube. So I divided everything by n cube. And then you can see that what you have here is, look at the one I just boxed. So you have sine square n over n cube less than 1 over n cube, right? And you can let this thing to be your an. Let this thing to be your bn, right? And then you can see that what we have is, we have this thing is equal to 0, right? 0 less than a sub n and less than or equal to b sub n, right? Which match the statement here. And then if we know that summation of bn converge, then we can conclude that an converge. So we consider the summation of bn when n start from 1 to infinity, which is the summation of 1 over n cube, right? And this thing is convergent, right? This thing is convergent because this thing is p series where p equal to 3. So that means it is convergent by p series. So bn, summation of bn converge. So it imply that summation of an, which is summation of sine square n over n cube, must be convergent to. Because of the comparison test. And that is how we use the comparison test. So you can see that the hardest part is 1 over n cubed come from nowhere. So the hardest part for comparison test is, yes, you have to make a comparison by your own. That is why it is so hard. Alright, let's do one more example on this page. So I have a summation of arctan n over n. So how can I do this question? So we need an inequality for arctan, right? That is the thing. So let's look at the graph of arctan first. So if you have n here, n here, and then you have fn here. So the graph of arctan gonna be like this, right? Oops, sorry. The graph of arctan. Alright, arctan n is a graph like this, and we know that the behavior of arctan, the limit is going to be pi over 2 when n go to infinity. And you know that arctan 1 is equal to pi over 4. This is because tan pi over 4 is 1. That means when n equal to 1, well, your arctan is pi over 4. It means your arctan 1, your arctan n, it's going to be at least pi over 4 when n is bigger than or equal to 1. So when n is bigger than or equal to 1, you see the one I highlight in green, when n is bigger than or equal to 1, you can see that your graph just already passed the point where the y value is pi over 4. So when n is bigger than 1, your arctan n gonna be bigger than or equal to pi over 4. So you have this statement. So from the graph, we have arctan n bigger than or equal to pi over 4 for any n that is bigger than or equal to 1. And then we need arctan n over n, so I'm gonna divide everything by n. Right? And then after that, now I have an inequality here. And then I am going to consider summation of pi over 4n. And this thing is pi over 4 times summation of 1 over n, right? Well, this is a harmonic series, or we can call this is p series where p equal to 1. So this thing is divergent because this is p series where p equal to 1, or you can call harmonic series the same thing. So this is divergent, so it means when you have your smaller series that is divergent, so the big one, the one that dominates this series, is also divergent. So we conclude that summation of arctan n over n is also divergent. Alright. I know this is not easy, but well, that is how comparison tests work. Alright, let's do 2 more examples before we stop this clip. Alright, let's do part C and part D. So part C, I have summation of 1 over 3 to the n plus 1 here. So we're gonna just make a comparison test with 1 over 3 to the n. That is the easiest way to do. So first, we know that, well, 3 to the n plus 1, this is always bigger than 3 to the n, right? And then if you do the cross multiply or something like that, so you're gonna have 1 over 3 to the n bigger than 1 over 3 to the n plus 1. right? This is what we have. And then you can see that, well, this is the thing you want, right? So this is our AN and this is our BN. So you have BN equal to 1 over 3 to the n. So we're gonna consider our summation 1 over 3 to the n, where n start from 1 to infinity. And this thing is summation of 1/3 to the n power when n start from 1 to infinity. And this is a convergent series, right? Because it is what? It is geometric series, right? It is a geometric series because you have geometric series r equal to 1/3, so that is less than 1. So this is geometric series that absolute r less than 1, so it is convergent. And when you have a convergent sequence that dominate the thing that you wanna compute, so by comparison test, summation of 1 over 3 to the n plus 1 here, this is also convergent. All right, done. All right, the last question for this topic. So I have summation of log n over n cube, where n start from 3 to infinity. All right, so how do we do this thing? So again, let's look at the graph of log n. So this is your function, this is your n, and then the graph of log n gonna be like this, right? This is the graph of log n. Well, you can see that when n equal to e, so this is the function is equal to 1 because log e equal to 1, right? And e is approximately 2.7, right? And that's mean if you start from n equal to 3, this thing gonna be a little bit above 1, right? At the point n equal to 3. So it's mean log of n, it's always bigger than 1 when n is bigger than or equal to 3, right? If you start from n equal to 3, here, start from n equal to 3, you can guarantee that your log n is going to be bigger than or equal to 1, right? Because it already passed number 1. So that means you can use this inequality. So we're gonna start from there. So we know that log n is bigger than 1 when n is bigger than or equal to 3. So now we're gonna do log n over n is bigger than 1 over n, right? When n is bigger than or equal to 3, because you just divided everything by n. And then now you can observe that this thing is your an, right? This thing is your bn. So now you have the inequality an greater than bn. So now we're gonna consider summation of 1 over n, which is our bn. N start from 3 to infinity. And this thing is a divergent series, right? This is a divergent series because this is p series when p equal to 1, or this is a harmonic series, the same thing. So p series, p equal to 1. All right, this thing is divergent, so that's mean by comparison test, summation of log n over n, n start from 3 to infinity, is also divergent, right? Because you have something that is smaller, that it is divergent. So the bigger thing, the thing that dominate, must be divergent as well. All right, so we're gonna stop this clip here because it's getting long. And then on the next clip, we're gonna look at the limit comparison test.